What's up, mathematicians? Justin here, and in this video we're going to be talking about the angle sum of a triangle. Now, before we get into the angle sum of the triangle, I'd like to talk just a little bit about measurement in general and some of the different types of measurements we can make. So I happen to be a bit of a measurement nerd. I love measuring things. What can I say? And there are all sorts of different things that you can measure. For example, time is something that we measure all the time, no pun intended. But we can use a watch to measure time, or a clock. Weight we measure. We step on a scale to measure our weight, or if we're cooking food, we might put it on a baking or a cooking scale, measure weight. Temperature is something that we measure as well. Volume or light intensity. I have a little decibel meter here, so I can measure approximately how loud. Let me switch this over here. So I'll just talk a little bit. You can see my voice comes in somewhere in the 70 to 80 decibel range for the most part. So yeah, I can measure volume with decibels. I can measure light with a light meter. And there are other things as well. In geometry, however, we tend to focus on measuring, we tend to focus just in general on spatial objects and properties. And so when we measure, we're typically taking spatial measurements. So for example, the loudness of my voice is not really a spatial measurement. So what are spatial measurements? Distance, of course, is the main one that we do the most of. And I love measuring distance as well. So, we can go across different levels. So if I'm measuring something really want to be super precise and it's a smaller object, I can use a caliper. I don't know if that's coming in focus or not. Too bad. Let me put it in front of my face. Does it come into focus then? No? Can't? Oh, there we go. All right, so this is my caliper that I can use to take very precise measurements. Step up from the caliper, we got the ruler, right? We can measure down to, this one's got down to 1/2 millimeter. That one goes down to 1/2 millimeter. Then something bigger than that, we got the tape measure, but why stop at a 2 meter or 6 foot tape measure? You can go to a bigger tape measure. When I'm doing, carpentry, woodworking type projects, I typically will use this tape measure. I'm measuring things in my yard, trying to plan things out. That's like a 30-foot tape measure. What if I want to go really big? Here is my 30 meter or 100-foot long tape measure, and you can get ones even bigger than this. The point is, there are all sorts of tools for measuring length, and one of the reasons for that is length is a really important thing to measure. Once we go beyond length or distance, the next dimension up is area, and past that we get 3 dimensions, which we use volume to represent 3-dimensional space. Typically, area and volume are not measured directly. We could do that. Like, we could measure area by taking a 1 centimeter or 1 foot or something square and then just like repeating it. Probably wouldn't end up being as accurate as measuring it, measuring the different distances and then using a formula to calculate the area. But we could do it that way. And then with volume, typically if we want to find a volume of a room like the one I'm in, I'll measure the height of the room, the length, and the depth of the room, and I'll multiply those out to get the volume, because rooms are typically sort of box shaped. But you can measure things in other ways. Volume, for example, there's the famous situation that Archimedes is associated with Archimedes, the famous Eureka moment, right? Where Archimedes realized that he could measure volume by putting something in water, and the amount of water that's displaced will tell him what the volume of the object is. And so this Eureka moment of Archimedes, which you probably heard about in grade school, is an example of measuring as well. It's measuring volume. But yeah, as I said already, typically we do measurements of area and volume by using formulas, and rather than measuring them directly. And as I mentioned, I think in a previous video, trigonometry is also another way to measure length when you can't measure something directly. Okay, but is that all? I think I mentioned a couple of videos ago that there's another type of measurement that we do all the time in geometry. And I told you I was going to tell you what it was. Can you think of it? Well, the other type of measurement that we do all the time in geometry is we measure angles. So what is an angle? So angles can be thought of as representing some rotation in space. We measure angles using a protractor. And in this class, we're going to consider angle measures from 0 to 180. You can consider angle measures beyond, outside these bounds, but in a typical high school geometry class, you really just focus on angles that are measured anywhere from 0 to 180 degrees. Okay, let's go ahead and draw and measure an angle. So first thing that we'll need is a line segment. And so I'll just start at this point. That will be where the angle is. And from that point, I'll just go ahead and draw a line outwards. Okay, now I'm going to rotate my straight edge with respect to that point right there. So I'm going to make sure that point stays on the straight edge, but I'm going to rotate it up. And then I'm going to draw another line from the point along the straight edge. Okay, so you see here I have this line and then a rotation up to that line. Now, how far did I rotate in order to draw this line? Well, that's what I use the protractor for. So let's pull out the protractor and, oh, that's unfortunate. I'll have to measure it this way because it's running to the edge of the paper. Okay, so then I just line it up so the point where the angle is at is right here, and then I start from 0 up to 10, and it's less than 20. It looks like 2 degrees less than 20. So that would be an 18-degree angle. So the straight edge rotated 18 degrees from the first line in order to make the second line. Okay, now before we measure the angle sum of a triangle, I want to talk about some of the assumptions that we have made so far in this course. And so here are some of the assumptions that we've made. So first of all, similar triangles exist. When we wanted to measure the height of the tree, we took advantage of similar triangles and the fact that they're proportional. So similar triangles exist and their sides are proportional. This is necessary for trig and problems involving similar shapes, like the triangles we use to measure the tree. Another assumption is that right triangles all have the same angle sum. We decided on 180 degrees. We could not do trigonometry in the way that we did it without this assumption. Another thing that we mentioned briefly is this idea that, well, maybe all triangles have an angle sum of 180 degrees. And then also for one of the trig applications with angle of depression from the lighthouse, I use this fact. The angle of elevation for an observer is equal to the angle of depression for the object, and vice versa. The angles in this case made by parallel horizontal lines, and these types of angles are called alternate interior angles. So we're assuming that those were equal in order to solve that problem. Finally, we also assume the existence of squares and rectangles. This enables us to make grids to base our concept of area on. The basic unit of area is a square unit, and if squares don't exist, then this idea of area doesn't work at all. We don't even have a starting point, and we would have to go back to the drawing board. This last one is one that a lot of people take issue with when I bring it up. So for example, people say, well, you're questioning whether squares and rectangles exist. I mean, we just defined it. I drew one I can draw one on a piece of paper. There's a rectangle. Obviously it exists. We define a rectangle as a quadrilateral with 4 right angles. How can you say it doesn't exist? Well, 2 things to say in response to that. Number 1, just because you define something doesn't mean it exists. I could come up with a definition for unicorns, but that doesn't bring unicorns into existence. Number two, you say that you can draw a rectangle. How do you know the thing you drew is a rectangle? Maybe it just looks really close to a rectangle. Maybe those lines look straight and the angles look super close to 90 degrees, but maybe they're not actually perfectly 90 degrees. So that may seem a little pedantic, but if we want to get down to really precise, factual geometric truth, these are things that we do need to think about. Now let's focus on this idea of the angle sum of a triangle. And let's just start by drawing a triangle. And I encourage you to do this as well in your notes. So I'll just pick 3 points here, here, and maybe one over here. Okay. Now we'll use a straight edge to connect all these 3 points. Okay, now let's use a protractor to measure all the angles. So I'll go first to this angle here and line it up. So this to me looks like 39 degrees. Start from 0 and it's just 1 degree shy of 40. Okay, so 39 degrees. Let's measure this angle here and we'll line this up. And looks to me like 38 degrees. So again, we start here, 0, 10, 20, 30, 2 degrees shy of 40. So 38 degrees here. And now let's go to the top and let's line this up here. Okay, that looks pretty good. All right, and now it looks like this is an obtuse angle. It's greater than 90 degrees. So we go 0 up to 90, 100, and then we go, this is 100, 101, 102, 103. So it looks like 103 degrees. Okay, so this will be 103 degrees. Let's go ahead and add up these 3 angles. So we have 103, 37, and 38. And let's see, 3 plus 7 is going to equal 10, plus 8, 18. And then 1 plus 3 is 4, plus 3 is 7. And then we bring this 1 down, and we get 178 degrees. Okay, so that's pretty close to 180, right? But it's not quite right. Why am I off? Well, you know, when I did the measuring here, I probably just didn't perfectly line it up. You know, maybe if I moved it over a little bit more, that would be like 38.5, and maybe I don't know. The point is I'm using an imperfect measurement, but I got something close to 178 degrees. So is this evidence that this triangle has an angle sum of 180? It's evidence that it could be pretty close to 180. And even if you measure and you get exactly 180, that doesn't mean that that it's accurate down to a small tolerance. Maybe it's just accurate to within a degree or a couple of degrees. Depends how precise your measurements are. There will always be some kind of tolerance there. Okay, so what could we do to be sure that all triangles had an angle sum of 180 degrees? Well, this right here hasn't given me more confidence because, you know, I was off by a little bit. So yeah, is there a way that we could assure ourselves that triangles actually do have an angle sum of 180 degrees, that all of them have that angle sum? And we have a really important, powerful tool in mathematics for knowing things, and that tool is called proof. If we can write a proof if we can come up with a proof that triangles have to have an angle sum of 180 degrees, that can give me way more confidence than just measuring and coming pretty close. Okay, so at this point, I'm going to turn it over to you. And I'm going to recommend that you pause the video and spend a little time on this. So we're going to look at it in 3 levels. First, there exists a triangle with an angle sum very close to 180 degrees. Second, there exists a triangle with an angle sum of exactly 180 degrees. And third, all triangles have an angle sum of exactly 180 degrees. Try to prove the first one. If you think you got that one, try to do the next one. If you got that one, go on to the third one. And for each proof, determine as best you can what assumptions that proof relies on. Now, for the first one, you might say that the measurement that I just did here is evidence enough that there is a triangle with an angle sum very close to 180 degrees. So yeah, I mean, this is evidence for the first one. But what I'd like you to do is maybe come up with evidence that you could come extremely close. Like, can you come up with a proof that you can get really, really close beyond just the tolerance of a device like this? And then move on to the other 3. And I'll go ahead and talk about a few attempts that you might have made or that I've seen students make. But first, give it some time, work on this on your own. Okay, let's start by thinking about the really close, attempting to demonstrate that. So one method that I see students coming up with is this. Let's draw a triangle with an angle that's really, really close to 180 degrees, right? And so that might look like this. So I'm going to rotate this just a little bit over. Okay, so you see there, that's a really big angle. And then let's go ahead and connect these 2 endpoints. Okay, so that right there is a triangle. It meets the definition. It's got 3 sides. I drew them with a straight edge, so we'll go ahead and say they're straight. And this angle here, barely fit the thing in there, that angle is really close to 180 degrees. These other 2 angles on the ends are really small. And you can imagine how the bigger this angle gets, the closer this big angle here gets to 180, the closer these get to 0. So what that means is that you could have a really, really skinny triangle that's an angle sum very close to 180 degrees. What are you assuming here? I would say not too much. You're assuming that the evidence shown on the piece of paper, like the picture, is something that's reliable for making an argument about an abstract thing like a triangle. And now let's look at another approach that a student came up with. One of my students came up with last year that I thought was pretty interesting. This student said, okay, let's start by, and this came out of me questioning their ability to draw a rectangle, which I'll get to in a little bit. But the student was like, okay, well, let me at least just draw 2 right angles like this. And so here are the 2 right angles. Okay, so we won't worry about if I connect these 2 sides over here, if those angles could also be right. Just forget about that, but just go ahead and give me that I can make 2 right angles like this. Okay, that seems reasonable enough. So then the student said, okay, now let me divide this angle in half. So I said, okay, we'll divide that angle in half, kind of like this. And the student said, okay, now let's divide it in half again. So maybe something like that. And the student said, well, now let's divide it in half again. And so maybe somewhere in there. Okay, so the idea here is the student's claiming they can just divide this angle in half over and over and over. And as they do, this angle here is going to get closer and closer to 0. This angle here is going to stay 90 degrees. And this angle here, as it gets closer, as this line gets closer and closer, this angle is going to get closer and closer to 90 degrees as well. So this is another argument showing that you can have a triangle with an angle sum very close to 180 degrees, where this is a right angle, this is almost a right angle, and that's almost 0. Maybe it is 180 degrees, but we can show from this argument that it could be at least very close to 180 degrees. What does this argument rely on? It relies on the assumption that you can construct or you can create right angles, and it also relies on the idea that you can divide these angles in half, and it relies also once again on the fact that a diagram on a piece of paper is helpful in demonstrating things about abstract objects, abstract mathematical objects. The fact that we can see these lines, on the paper, and we can say, oh, those also exist in this abstract realm. Okay, so that's a couple examples for the first one. Now let's look at the second one. Prove that there is a triangle with an angle sum exactly 180 degrees. And one of the most common attempts that I get from students in this is to say, okay, let's start with a square. And they say, okay, here we go. Here's a square. And then they say, okay, now I have a square and it has 4 right angles. Now we'll go ahead and draw a line cutting the square in half. Well, 4 right angles add up to 360 degrees, 90 plus 90 plus 90 plus 90. And now that I've divided those 360 degrees in half, there must be 180 here and 180 here. Therefore, this triangle must have an angle sum of 180, and this triangle must have, this triangle must have an angle sum of 180 degrees as well. Okay, so my first criticism is this. I'll go ahead and give you that you can connect this point with this point. But when you do that, do you know for certain that this angle is actually divided in half? Do you know, like, maybe this triangle up here has an angle sum that's greater than 180 degrees, and this triangle over here is left with an angle sum that's less than 180 degrees. How can you actually say that it divides the angle in half? And you get half of the angle sum here, half the angle sum there. So they say, okay, fine. What if instead of just drawing that, let's go ahead and, if you'll allow, for example, up here that you can divide an angle in half, I'll go ahead and just draw, divide this one in half and divide that one in half. But now they're assuming that those two meet in a straight line. And I say, well, wait a second. How do you know when you divide this one in half, it doesn't go like up here, and when you divide this one in half, it doesn't go, sort of down here? How do you know those two lines actually meet? And even if they meet, how do we know they make one single straight line? Okay, so then, typically at this point, they're like, okay, fine, and sort of give up and try another thing. And I'm like, well, wait a second, I have another criticism as well. How do you know that a square, a quadrilateral with 4 equal sides and 4 right angles, exists? How do you know that the thing that you have there isn't just really close to a square, but not actually a square? And then they start to get pretty, typically, some students start to get pretty frustrated, and they're like, what do you mean? Squares don't exist? We've been learning, I learned about squares when I was 2 years old, and since then they've been continuing to show up in books and school and other things like that. Okay, so you've seen things that people have said are squares. Sure, but that's not a proof. That's not a proof that squares exist, right? Then you can do similar things with a rectangle. I'm not going to go over that right now, but basically that would be, maybe something you could use to try to prove that all right angles have an angle sum of 180 degrees. You can, use rectangles to try to prove that. But one place where I see students sort of fall into a logical trap here with these squares and these rectangles is they'll make this claim, and I've had students even with an irregular quadrilateral say, oh, hey, look, a quadrilateral has an angle sum of 360. So when I divide it in half, the angle sum is 180. They'll say, well, just forget about the right angles. This quadrilateral has an angle sum of 360. Okay, so sure. What is your evidence for, like, how do you know that's true? And it turns out, so we'll say the quadrilateral angle sum equals 360. And they want to use that as evidence to show that the triangle angle sum equals 180 degrees. Well, the problem is the fact that quadrilateral angle, the angle sum of quadrilateral is 360, actually depends on the triangle angle sum. So I've seen students, try to make these arguments implicitly using the triangle angle sum, like, for example, with right angles, two right angles making a rectangle, saying like, oh, I guess I'd have to draw it to show it clearly, but it's just basically using facts that they've assumed about right triangles and triangles in general to show that, certain things are true about rectangles or other quadrilaterals, and then using that to prove the triangle angle sum. And you can see the problem here, right? Which is that you're using this fact to prove this fact. So you use this fact to prove this, and then this to prove this. This is what we call circular reasoning or circular logic. This doesn't prove anything, and this is, a logical fallacy. This is a problem, and we wouldn't want to be using logic like this to prove anything. That would not be reliable. Okay, so finally for number 3, and there are a number of ways to do number 3 for all triangles. The one that I usually see students come up with, or maybe they find it in a book or on the internet, and they'll bring it to class and they'll say, hey, look, what about this option? We'll take a triangle and extend the lines past the points, and then we'll go ahead and draw a line here that's parallel to the first line. Okay, so we'll say this line here is parallel to this line here. Then they'll say, okay, look, this angle here is equal to this angle here. We'll call this angle 1. I guess I don't need the angle sum or the angle symbol if I put it there. Or actually, I'll use alpha, the Greek. Okay, so we'll say this is angle alpha, and then that means this is angle alpha as well. Then they'll say, oh, well, this angle here is equal to this angle here, and so we'll call these angle beta. And then they'll say, okay, well, then we'll look at angle gamma here. Okay, so the angle sum of this triangle, so the triangle angle sum in this case is equal to alpha plus beta plus gamma. Alpha plus beta plus gamma. But this alpha is equal to this alpha, and this beta is equal to this beta, and beta plus gamma plus alpha, you can see here, add up to a straight line. In other words, they equal 180 degrees. Well, if the angle sum equals alpha plus beta plus gamma, and alpha plus beta plus gamma equals 180 degrees, that must mean that the triangle angle sum does in fact equal 180 degrees, right? Well, this is a very nice argument, but there are still some issues that we can bring to light here. First one is this idea of constructing a parallel line. First of all, how do you know parallel lines exist? Second, how do you know that you can construct them? And the next issue is that, okay, let's go ahead and say you can construct parallel lines, they exist. How do you know just from the fact that they're parallel that these two angles are equal? Maybe it's something you heard, maybe it's something that looks right, maybe it's something that just intuitively seems right to you. But if you remember from the last video, things that seem intuitively correct or clear aren't necessarily true. And so we have to be careful just relying on our intuition here. And typically students don't come in with evidence for why those two angles have to be equal to each other. And so usually by this point, when I poked holes in all these different arguments, students start getting a bit exasperated with the whole thing. And that's kind of the point, actually, right? Is to really push at these things to the point of having students even ask themselves, well, how do I know anything? Like, how do I know anything is true? In fact, one student shared with me a comment that So when I did this lesson with a class about a year ago, and we spent pretty much the whole class poking holes into different proofs and such. And finally, I had a student who got a bit exasperated with the whole situation and say, hey, look, if you question everything, we can't prove anything. And she was right. And when it comes down to it, that's really the whole point of this exercise, of this lesson. And I was so happy to hear the students say that, because that's exactly the point that I'm trying to get across. You can't prove anything without first making some assumptions. If you question everything, if you don't allow anything in without just saying, well, okay, I'm just going to go ahead and believe this is true, then you are, basically dead in the water. That you can't make any progress. So in order to be able to do mathematics, to be able to prove that things are true, you have to start with some assumptions. And once you have those assumptions, you can build on them using logic to prove that certain things are true. And so that's what the next unit is going to be about, starting to look at these ideas of logic and how we can build up a structure to prove something like the angle sum of a triangle, that all triangles have an angle sum of 180 degrees. So that's the end of this unit. We're wrapping it up here, and we're going to move on and start talking about logic and how we could prove certain facts are true. Thanks for watching, and we'll see you in the next video.